Welcome back to Elements of Chemistry. Today we're going to talk about mixtures. A mixture can be a mix of elements, compounds, and other mixtures. So a mixture is a mix of all sorts of different things. So let's look at some particle diagrams to kind of identify what these things would be. If I were going to show an element, I would show it as a single colored dot, um, just a single ball. A compound would have a connection. They would be touching, showing a chemical bond. So that connection right there shows a chemical bond. And it's of two different elements. So this could be like sodium and chlorine. If I had something like oxygen, which is an O2 of the same element, I would have them connected, but they would be the same color. So I would like have two pinks connected to each other if I wanted to do what we call a diatomic molecule. The key is it's touching. And that would still be classified as an element because that's the purest form that this substance can come. So if I look at this next one, I can see it's a mixture. I've got this compound, the blue-black, and I have a compound gray-purple. And I don't seem to have anything else in there. So this is a mixture of two different compounds. So when you look at a mixture, mixtures can be classified on whether or not how they can be separated. A mixture that looks the same throughout is called a homogeneous mixture. Things like coffee, wine, air, brass, steel, natural gas, vinegar, even blood are called homogeneous mixtures because when you look at air, you don't see the different chunks, the different parts of it. Whereas in a heterogeneous mixture, let's look over at those. If they look different, we call them heterogeneous. A sandwich, chocolate chip cookies, you can actually see the chocolate. Pizza, you can see the different ingredients. If you don't like mushrooms, you can pick it off. It's easy to separate. Soda with ice, you can take out the ice. Tossed salad, you can pick out whatever part you don't like. They're easier to separate. Okay, so they're classified as homogeneous, which looks the same throughout, heterogeneous, which looks different throughout. So now if we look at our homogeneous mixtures, we can have a solution or a colloid. How these are classified is a little bit different. They both look the same throughout. A solution is the best mixed. A colloid will exhibit what we call the Tyndall effect. A Tyndall effect is when you shine a beam of light through it and you can see the beam. It's like when you're driving in the fog and you can see the beam of your headlights. The water molecules in fog, moisture, will scatter the light. So that's a Tyndall effect. A solution, it's so well mixed that that beam of light just goes straight through. So the Tyndall effect is how we identify a colloid. If you have smoke in the air, you can see the lasers shine through it. Okay, so those are for homogeneous. A heterogeneous are generally classified as suspensions. Now, a colloid could also be a suspension. We call it a colloidal suspension. So colloids are kind of in the middle here. A suspension, things will settle out. This is like sand and water. The sand will settle out due to gravity. Little kid's antibiotic that you have to shake up before you give it to the kid, those are always suspensions. A lot of your medicines that they've had to make into a liquid because people couldn't swallow the pill are suspensions. Pepto-Bismol, great suspension. Okay, so when we're looking at how to separate these, well, obviously a suspension is going to be the easiest to separate because you can see the pieces. But let's look at it. If you have a solution, what can you do? You can evaporate it. You can separate it by just letting the solvent evaporate off. Because when you look at a solution, it's a mixture of a solvent and a solute. They combine to make the solution. If you evaporate off the solvent, you're left behind with the solute. A good example is Kool-Aid. You make Kool-Aid by adding flavor crystals to water, and if you've ever let it sit and evaporate away, you get the flavor crystals back. Some people will use Kool-Aid when they make rock candy. Distillation and fractional distillation, they're very similar. Okay, in a simple distillation, you're separating it based on boiling point. So physical properties allow us to separate things. In a distillation, you've got your solution in a flask. You're going to heat it up, cause it to boil at a certain temperature. Watch the temperature. Each solvent's going to come off at a different temperature. You'll collect the gas. It will travel through a condenser, which is a jacketed container, usually using cold water. So cool water comes in, cool water goes out, and it causes it to condense back down. We'll distill water this way so we get really, really pure water. What comes off is what we call a distillate. And eventually you're going to get a bunch of sludge stuff down here in the bottom. Caribbean islands will also often distill salt water to get fresh drinking water. Unfortunately, that is very, very energy consuming, not good for the planet. So there's other ways that they now get it. But that used to be how a lot of Caribbean islands got their drinking water because they couldn't rely solely on rainfall. A fractional distillation, or you can do a fractional crystallization. A fractional distillation is where you take a mixture and you heat the mixture up to a very high temperature. You let it rise, the gases, vapors will rise in a column, and it will collect off at different temperatures. So here, if we take crude oil, which is a common example for a fractional distillation, you heat it up to about 400 degrees Celsius. Fuel oil, heating oil for homes, comes off at about 370. If you collect the height of the column at 300, you're getting diesel fuel. 200 kerosene, 150 would be our gasoline, petrol. And then way up at 20 Celsius, we're getting our butane and propane. Anything that didn't boil at 400, that's your lubricating oils, your paraffin wax, your asphalts, those get pumped out the bottom. So fractional distillation uses heat. Fractional crystallization is where you're going to be cooling it down and taking things off at different temperatures as they cool. Chromatography is a fun one, and you hopefully will get to do this in a lab. Chromatography takes into account the polarity of the molecules. More graphic here. So you'll do a plate, you'll have a spot where you'll put your solution that you want to separate, and you'll put it in a chamber. It's usually a solvent, and it usually has some type of cap over it. So we're keeping it very humid in there. We're doing it with water, depends on what your solvent is. And over time, we'll see the substance separate out. The compounds that travel as far as, or as close to as far as the solvent, have a polarity close to that of the solvent. The ones that don't move very much have a polarity less than the solvent. So you can see that it'll separate out. This is really fun to try with ink and water, or ink and rubbing alcohol. And you can make some interesting flowers. There's some cool craft ideas online you can find. Now, colloids are a little interesting. Remember, colloids show the Tyndall effect. The particles will scatter light. One of the ways we separate colloids, like blood, is by centrifuging it. And we're going to kind of enhance gravity a bit here. We're going to spin it down. And we're going to get the larger particles are going to go to the bottom, and the supernatant, the liquid on top. So this is how we separate blood cells from plasma. This is a fun one. You can use a flocculant and a coagulant. This is mostly used in water treatment. I use it in my home aquarium. Sometimes when you clean your aquarium, the water looks less than clear and perfect. So you'll add a flocculant. And what a flocculant does is it grabs onto the impurities in the solvent and makes it clump together, and then it can settle out or be trapped in a filter. So let's talk about filtering, because that is the most common way that we separate things. We can also use electrostatic destabilization. Um, you're not going to see that super often. Flocculants, though, are kind of cool to do. Filtering is how we separate suspensions. We separate coffee grounds from the coffee by putting it through a coffee filter. When we do filtering, we're going to have a piece of filter paper, a funnel, and generally we're going to use an Erlenmeyer or a conical flask. We're going to stir up our suspension. We're going to pour it down into the filter paper. We're going to collect the residue, and what filters through is a filtrate. The filtrate's not always a pure solvent. We may have to do something else to separate out that filtrate, but this is the essential elements of how to filter. Screening is a common method that archaeologists use to remove large particles. We can use a separatory funnel, which also takes into account settling. Here we're separating a liquid, here oil and water. The oil, or the less dense liquid component, will rise to the top, and we can let the more dense, or in this case water, filter out the bottom. Separatory funnels are really cool, kind of delicate to work with. Hopefully you'll get to work with one in the lab. Decantation is one of our more common terms or ways of separating it. And literally it's pouring the liquid or the filtrate, supernate, off of the precipitator solid. And we'll do that by having it flow down a glass stir rod. Quite often you'll hold the stir rod, this is the stir rod here, against that little spout in your beaker, kind of hold it on with your fingers, and then the liquid will trickle down that into, and you can kind of block any of the solids from leaking down. It's just a faster way. A lot of people will decant off a lot of the liquid before they actually go and use filter paper. It speeds up the process. Hopefully your teacher will demonstrate how to decant. It's a really useful thing. Most people hear of the word decanting when they think about pouring off the liquid from like balsamic vinegars or wines, things like that, to remove the solids. Electrostatic attraction takes into account positive and negative charges. This is often used in recycling programs where they're trying to separate metals. You'll pull it down a chute, you'll have an electrified roll. Poor conductors will go one way, better conductors go another. Magnetism, you can separate some things just by putting a magnet through it. Be creative. When you're separating out a suspension, you're real, or any mixture for that matter, you're looking at the chemical and physical properties. Can you use melting point to your advantage? Can you use the boiling point to your advantage? Distillation. Can you use the properties of magnetism or electrostatic attraction? I mean, if you had to remove styrofoam pellets from a mixture of sand and salt, well, I would use electrostatic attraction and use a balloon, get some static electricity, and you know that the styrofoam will be attracted to the balloon. You can use magnetism to remove iron filings from that mixture. If you've got sand and salt, well, salt dissolves in water, use solubility, and then filter out the sand. Quite often you're going to be given in the lab a mixture that you're going to need to separate. Use the physical properties of that material to your advantage. This is talking about mixtures. Our next video is going to be covering the more purest parts of matter, elements, and compounds. I hope this video helped. Stay curious, be kind, stay safe, and have a wonderful tomorrow. Enjoy your day.